Welcome to part 2 of today's notes. This goes with page 11. On this page we're going to do something new. It's called rationalizing denominators. So there's an important rule that we all must follow. Radicals should not ever be allowed in the denominator of a fraction. So when we have one, what we're going to do is called rationalizing the denominator. What we're going to do is we're going to multiply the numerator and the denominator by whatever is underneath the radical for the denominator. We're going to take a look at the first exercise. Simplify each radical expression. We are still looking for perfect squares, so 4 is a perfect square. We're going to leave that alone. We're going to give it its own radical, the square root of 4 divided by the square root of 7. We're going to circle the square root of 4, which becomes the whole number 2 in the numerator, but the square root of 7, it stays the same. What we're going to next do is rationalize the denominator. We're going to multiply the top and the bottom of this fraction by whatever is the radical in the denominator, in this case the square root of 7. So go ahead and write a fraction, put a root 7 in the top and a root 7 in the bottom. We're going to multiply top to top, bottom to bottom. What's 2 times the square root of 7? That's 2 square roots of 7. What's the square root of 7 times the square root of 7? That is the square root of 49. And now this is a perfect square, which simplifies. 2 square root of 7 divided by the square root of 49, which is 7. Give it one last look. Does 2 and 7, does that simplify? It does not. Do these 7 simplify? One's under a radical, the other's a whole number. The answer is no, it does not. That's your finished, final, and best answer. Let's take a look at letter B. 6 and m doesn't simplify. So we're going to simplify it by separating the numerator and the denominator. The square root of 6 divided by the square root of m. There's no perfect square that divides a 6 aside from 1, which doesn't help. The square root of m is in the denominator. We cannot have any radicals in the denominator, so we're going to rationalize this. What are we going to multiply the top and the bottom by? The square root of 6 or the square root of m? It's the one in the bottom. Square root of m over square root of m. Since you have 2 m's in the bottom, that becomes an m squared. And the square root of m squared will become the perfect square, or will become the whole number, or the whole power of m to the first. The top, the square root of 6 and the square root of m, since they're both numbers or variables underneath radicals, their product goes underneath the same radical. The square root of 6m divided by m. Outside m's and inside m's do not cancel each other out, so this one is completed. Middle row. We are still looking for squares. 7 over 8. We're still trying to simplify fractions first. Nothing simplifies. So we're going to separate it. Square root of 7 divided by the square root of 8n. Now 8 does have a factor that will be a perfect square, so why don't we go ahead and simplify that first. The other thought is just to multiply the top and the bottom by the square root of 8n, which we could also do. I always like to simplify first, like our special note says. 8 can be broken into a 4 and a 2 and a square root of n. Circle the 4. The square root of 4 in the denominator becomes a 2. And then we have the square root of 2n. The numerator has a square root of 7 in it. Now it's time to rationalize the denominator. We're going to multiply the top and the bottom by just what's underneath the square root in the denominator, not the whole denominator. What's underneath the square root, which is just the square root of 2n. Take a look at the numerator. 7 times 2n is 14n in the numerator underneath a radical. The 2 on the outside stays on the outside. 2 times 2 is a 4 underneath the radical because the two 2's are under radicals. The n and the n under radicals make n squared under a radical. Let's keep going. Since 4 is a perfect square and n squared is a perfect square, they come outside of the radical when you square root them. Square root of 14n, the numerator, stays the same. The bottom, we started with a 2 on the outside. The square root of 4 is another 2 on the outside, and the square root of n squared becomes an n on the outside of a radical. One last step as we work from right to left. The numerator again stays the same, 14n. The denominator, we're going to multiply the two 2's to make a coefficient of a 4 and an n. So multiplying by the radical from the denominator makes the denominator no longer contain a radical. That rationalizes your denominator. One last look. 14 does not have a perfect square that divides it and is not an even power, so this one is completed. Take a look at letter D. Again, simplify fractions and look for perfect squares. This one is tricky. This one I want to take a look at. 36 is a perfect square. So I don't want to disturb that. I'm going to leave this 36. I'm not going to cancel it to make it 1/18. I think that would make our job more difficult. So for the coefficients, we're not going to simplify that fraction. For the powers of p, however, we are going to simplify the fraction because there's 4 more in the top, and we want the powers to be even. So one of these we're going to simplify. The others we're not. We're going to simplify only the variables. So we're going to leave the 2 over 36 the way it is because we noticed a perfect square. And we're going to simplify the p power to become p to the 4th. These are perfect squares. If you didn't notice that, the method could be a little bit longer if you try something new with something else. Square root of 2, p to the 4th, divided by square root of 36. I'm going to circle each of these. The square root of 2 stays underneath the radical, and the square root of p to the 4th becomes the p squared on the outside. I'm going to write that first. The square root of p to the 4th is p squared. The square root of 2 goes next to it. The square root of 36, and the denominator just becomes a 6. Although the 2 is under the radical and the 6 is not, those do not cancel. Nothing else to simplify. I think that made our job easier. I can imagine doing it the other way. So we have like p squared, and then we have square root of 9, square root of 2. Actually, this isn't so bad here. We have p squared over 3 root 2. Rationalize the denominator. So we have p squared root 2 over 3 square root of 4, p squared root 2 over 3 times 2, which is 6. We get the same answer either way. So if you wanted to reduce it first, you're still going to come up with the same answer. There's not one standard way to do each exercise. So that's why we give you a note. Look for opportunities to cancel and look for perfect squares. So I have an opportunity to cancel this one. 2 goes into 6. Neither of these is a perfect square, so we can get rid of that. We're going to keep the negative 5 on the outside first. 2 goes into 2 once, and 6 3 times. So underneath the radical, we have 3 over n. We're going to separate this into two different roots. Negative 5 stays on the outside, square root of 3 in the top, square root of n in the bottom. We're going to rationalize the denominator because we have a square root of n in the bottom. We are going to multiply the top and the bottom by the square root of n divided by itself. Coming on down. So we have the negative 5 times the numerator square root of 3 underneath the radical, square root of n. To make the product, square root of 3n underneath the same radical. The square root of n times the square root of n is the square root of n squared. That's a perfect square because it has an even exponent. Let's finish this out. Negative 5 square root of 3n divided by n. If it's okay with you, I can write negative 5 square root of 3n all divided by n. That's like as if I put the 1 and multiply the tops together and the bottoms together. So it looks like this. You might see an answer written like that instead. Alright, take a look at this last exercise. This one is a bit complicated. That's why we saved it for last. These two radicals are already separated. But if you remember the division property of square roots, we are able to put these back together so that we can cancel this x with one of those x's. You're allowed to do that. If all of the time we've been separating radicals and fractions, we actually could do the opposite and put these together. So maybe my first step would be to do this. Leave the 8 on the outside of the numerator, put the square root of x over 32x to the third so that I can simplify these x's. Just like outside terms can cancel outside terms, inside or underneath radicals, radicands can cancel themselves as long as their indexes are the same. So we have 2 more x's in the bottom. So let's cancel the x in the top. You cannot have a fraction with an empty numerator, so we're going to replace the x in the numerator with a 1. We're going to take 32 and keep it the way it is. We're going to make x to the third and x squared. Now we're going to separate our fraction into 2 separate radicals, even though we just put them together a step ago. 8 times the square root of 1 divided by the square root of 32 divided by the square root of x to the second power. So we know this is a perfect square. Does 32 contain a factor that's a perfect square? I'm going to copy this all the way on the left. 8, the square root of 1 is 1. The square root of 32 can simplify as the square root of 16 and square root of 2. And the square root of x squared, well, I can circle that and I can make that an x. Where am I going to put that x? I'm not going to put it at the end. I'm going to put it in the front. We could make this one big fraction. As we saw in the last step of the last exercise, numerators multiply other numerators and so do denominators. I'm going to simplify the square root of 16. When I do a rewrite, we're going to multiply the 8 and the 1 together. We're going to simplify the square root of 16 to become a 4. The x is already on the outside, and I have a square root of 2 underneath the radical. One thing I do notice, we still have an irrational number in the denominator, so we have to rationalize the denominator. But do you notice that there's a 4 and an 8 that can reduce? Why don't we go ahead and reduce that now? 4 goes into 4 once, and 4 goes into 8 twice. So let me recopy this. I have a 2 divided by x square root of 2. Still has an irrational denominator, so we're going to rationalize it. What are we going to multiply the top and the bottom by? Just the square root of 2, just the part underneath the radical. So we're going to multiply the top. 2 times square root of 2 is 2 root 2. Multiply the bottom. The square root of 2 times the square root of 2 is the square root of 4, with an x already on the outside. So it's x square root of 4. The square root of 4 becomes a 2 when you simplify it. So we're going to work on down. We have 2 root 2 from the top and 2x in the bottom. 2x in the bottom. Finally, we're at the last step. The 2 from the top and the 2 from the bottom, since they're both outside, now they may cancel. And our finished final result will be a square root of 2 over x. That was a lot of work. There are, like I said, other ways of doing this. But as long as you look for your perfect squares and look for even powers, they will simplify. That is pretty much the end of what I needed to cover on page 11. The bottom exercises are there for you to try out. I would appreciate if you would continue to do your homework. I will check your homework the next time I see you. Your homework will be on pages 12 and 13 in this packet. I do realize that you may have questions with this. Do the best you can and work together. I appreciate you, and I will do the best to answer those questions when I return and see you next. Take good care.